Obvious natural extension of this would be to find out the amount of negative charge that is present in the radiation. Okay, so before you get lost into the detail of all of it, let me quickly remind you what we are trying to do is we are trying to identify whether atom is the fundamental particle, indivisible part of the element, or there is more constituent of an atom, so that atom can be further divided into other substituent particles. So in that quest, what J.J. Thomson did was he did an experiment, and he has known up till now that you have few gaseous molecules in the chamber after making it almost vacuum, so that you are getting some radiation. Now this, as you can guess very intuitively, that this is a sufficient proof. What is happening is the source of that radiation is those gas molecules. So that gas molecules is actually breaking and giving you a radiation. Now if that would have not been the case, then the radiation would have no charges on it, because the gas molecules are neutral. If the radiation would have been just because of the gas molecules, the fluorescence would have been just because of the gas molecules, then the electrometer would not have detected any charge, or the radiation would have not been attracted to the positive plate. Now entire radiation is attracted to the positive plate and no radiation goes towards a negative plate. That means the radiation is actually being of only negative charge. Now from where that negative charge came? That negative charge has to come from the gas molecule. So this gave J.J. Thomson the idea that the gas molecules can be further broken down, the atoms can be further broken down, and that due to the breaking of that atoms, you are having something. He didn't know what exactly it is, but for sure the atoms are being broken down into some constituent particles, and that constituent particles he's thought that he has identified that this radiation is falling on the positive plate. So this means that radiation is having negative charge. So he was overjoyous. He was excited that he has found something. Indeed, he found something. And that something, as you would understand, is electron. So what happened is gas molecules broke. The electrons came, actually in a proper terminology, gas molecules ionized. And the electron came out of it, and that electron is constituting this cathode ray. And this cathode ray gets attracted to positive terminal in the positive plate or the anode, and that proves that the radiation is having negative charge. So the job will not end up here. J.J. Thomson have to go on, carry out his experiment, and as to find out the value of the negative charge, because qualitatively we know that the radiation is having negative charge, but the job would be to find out the amount of the negative charge which is being carried by the radiation. So he extended his experiment, he added magnetic field into it, and I'll tell you in short, and later I'll explain you how he did it. He found out the E/m ratio of the radiation. E here is charge. The representation in physics for charge is small q. This is general for any charge. We are talking specifically about electrons here, as you would know in a short while that this discovery is about electron. So the charge on electron is represented by small e. That's why I'm using small e here. And this m is the mass of electron. So he found out using this very experimental setup the value of E/m. That these radiation are constituted by particles. That particle will have certain charge. That particle will have certain mass. So he calculated E/m ratio. That was of the order of 10 raised to the power 11. So he did his job. He is coming very close to find out the charge and mass. But what he has done, he hasn't found the charge and mass individually of the constituting particle of radiation, but he is able to find the ratio of it, because this particular experimental setup doesn't allow to find the value of E and M individually. All you can do with this experimental setup, as he did, was to find the ratio. This is the maximum you can reach. Exact value cannot be found out using this experimental setup. It is not possible, and he was not able to do it. He found out the ratio E/m that was close to 10 raised to the power 11. Now, if the value is very high, you can see the ratio is very high, very, very high. Now, a value of a fraction could be very high if the denominator is very high, or the numerator, if the numerator is very high or the denominator is very less. See, numerator is E. E is charge. Now, this value could be very high either if charge is very high or mass is very less. Now, charge cannot be very high to reach the value of ratio to be 10 raised to the power 11. You know, 1 coulomb of charge is too much. As you know, the charge on electron, still we are discovering electron, but you know, it happened in 1897 and we are here in 2016. So you know the value actually. It is 1.6 into 10 to the power minus 19 coulomb. So 1 coulomb is a very high value of charge. And to make this ratio as 10 raised to the power 11, it will have multiple times of this value, the charge. That is a very high value. It is not possible that every tiny particle of this radiation is having that high value of charge. It is intuitive that a tiny particle like this cannot have such a high value of charge. So for scientist J.J. Thomson, it was easy to guess that the mass of this particle has to be extremely low to make the whole ratio very high. So he had this idea and he confirmed it with an indirect experiment that mass of this value, mass of this particle that constitute the radiation is indeed very less. And he did an indirect experiment. What he did, he brought a piece of metallic object in the way. So what will happen is, instead of radiation falling on anode, the whole of radiation will fall on this metallic object. And as you understand that anything that is kept in the way of radiation, it becomes heated. It gets heated up. Anything you keep in the sunlight, it gets heated up. Anything you keep in front of any kind of light, it gets heated up. Fine. Now, how does it get heated up? Radiations, the particle that constitute that radiation has certain kinetic energy. The kinetic energy is half mv square. That kinetic energy is converted to heat energy. Fine. And that heat energy heats up the object. Now somehow, if you're able to find the velocity of this radiation, and if you are able to measure the temperature rise, if you are able to measure the temperature rise of this object, and if you know the mass of the object and you know the specific heat of the object, then ms delta T will give you the amount of heat that it has absorbed. The amount of heat that it has absorbed is easy to measure. If you can measure the temperature change, if you know the mass, and if you know the specific heat of this object. So the amount of heat that this substance has absorbed is easy to find out. That amount of heat should be equal to the kinetic energy. Fine. And if you're able to measure the velocity of this radiation, which he did, and I'll tell you how he did, then you can find out the mass. Because if you know the heat energy, you know the velocity, and then you can find out the mass of that particle which is coming and colliding with the substance. So indirectly, he found out the mass, and he found out the mass to be 1,000 times less than that of hydrogen atom. And he was very close in his estimation, the mass of electron. So he did that, but this was an indirect source and this was an indirect calculation. He could not find the mass directly. But later, Millikan was another scientist. He performed experiment after J.J. Thomson. He found out the charge of the radiation, the charge of electron exactly. Independent of mass, he found out the charge. So once we have the charge and we have E by M ratio, then from here we can find out the mass. So that's a more authentic way of calculating the mass. And that's how we know the mass of the electron. One more thing, actually two more things. First, I told you why we have added this pump here. This you must know. The purpose of this pump is to decrease the pressure inside the air so that very few molecules are left inside. The first question that should have occurred into your mind, if not, then you should think why there has to be very less air molecules inside the chamber. What would happen if there are more number of air molecules or any other gas molecules inside the chamber? Will the experiment be successful? Tell me, think. Actually, the problem would be if you have more number of air molecules, you would know that air is a bad conductor of electricity. So what is happening is electrons are running from one electrode to another electrode. In the meanwhile, if you have more gas molecules, then those gas molecules will absorb that electron. And the electrons will not be able to reach to the other electrode because air is a bad conductor of electricity. And this is nothing but the flow of current. Electrons are moving. It's nothing but flow of current. So air being bad conductor for the flow of current, then this radiation will not be able to reach this coating. So the experiment will not be effective. That's why there has to be minimum number of electrons inside the air, inside the gas chamber. That's one. Second thing I wanted to tell you, after finding all these things, he did perform the experiment with various gases. Now you know that you have one gas, there is radiation, you find out the E/m ratio. Now you repeat the same experiment for another gas with the same values, everything's the same setup. You found out the E/m ratio comes again as the same value. You performed it with a third gas, E/m ratio, you calculated, you found out 10 raised to the power 11, same. Fourth gas, same. Fifth, same. Sixth, same. Seventh, eighth, ninth, 10th. All the gases that you have performed, the value is coming as same. Then what can you deduce from this result? Can you tell me? This E/m ratio coming same for all the gases for which you have performed the experiment, then what have you actually found out? You have found out something very, very terrific, which will become a landmark in physical chemistry. You have found out that this radiation and the particle which is constituting this radiation is a fundamental particle for the entire matter. You are changing the gas, but the property is not changing. That means it is exactly the same radiation. Otherwise, E/m ratio would have been changed. That means you are changing the gas, but this value is not changing. That means all the gases are made up of same fundamental particle. That means all the atoms are made up of same fundamental particles. So actually you have cracked into the problem of finding the atomic structure, because if you have found this, that all the atoms are made up of same kind of fundamental particle, then you have moved one step closer to decipher the structure of the atom. So this was a very profound, very profound discovery, that the E/m ratio of the radiation is remaining same for all the atoms. And actually J.J. Thomson gave the